but the only thing when we are talking about stability, we are always talking about stability with respect to some other thing. As far as that particular phase is concerned, it is becoming more and more stable with increasing temperature. Yes, yeah. Why should you think that more randomness means it should not be stable? Do you think you are perfect? So we are all stable. So it does not mean that imperfection means lack of stability. That is the reason why we are saying that either enthalpy or entropy alone cannot talk about stability. A combination of these two, which is the free energy alone, can tell you. So if I simply use only entropy concept, if you say that the more the lower the entropy, the more stable it is, that's not the right way of looking at. The more the lower the entropy, the more perfect it is. It does not mean that perfect means stable. I mean, maybe spiritually so. In materialism, at least we cannot say that. So that is why we are saying that when we say stability, it is only in terms of the free energy that we try to look at it. Enthalpy, for example, if that is the case, even the enthalpy wise, the lower the enthalpy, the phase is more stable in principle. For example, look at a case like the electrons around a nucleus in various orbitals. The closer the electron to the nucleus, the more stable it is. There it is only enthalpy that we are looking at, and that is why we are talking about X-ray generation, that when you knock off one of the electron from a higher shell, the electron falls into the lower shell. So there we are basically looking at the energy aspect of it, the bonding energies, isn't it? So basically when you look at or convert all these things into free energy term, it is the free energy that dominates, and that is what we have seen in the last class, and let us try to continue from there. So we looked at this, and we said if this is let us say liquid and if this is solid, we say that there is a temperature called Tm. You can call it as Tm or Tf, freezing point or melting point, depending on how you look at it, and below which you say the solid has a lower free energy than the liquid, and above which you have the liquid having a lower free energy, and that is why we say, we always can say that any phase with a lower free energy is more stable when you are comparing two phases. This is comparing two phases, and in principle if a particular system has a large number of phases possible, I should be able to put all of them. For example, if I am taking a metal like aluminum, what are the possible phases that I can think of in aluminum? Alpha. What is beta aluminum? If I take aluminum and keep on changing the temperature, increasing the temperature, what are all the possible phases that I can expect in aluminum? Anybody knows? Aluminum as a solid has only one structure up to its melting point. So it is only one single phase up to its melting point, and from the melting point up to its boiling point, it is one single phase which is a liquid, and then from the boiling point onwards you can call a gaseous aluminum. So if I want to bring the third phase, you can call it as a third state of matter, and thermodynamically any state of matter can be even called as a phase. How do you define a phase, by the way? One of you talk.
Chemically homogeneous, physically
Distinct. Correct. So as long as it is chemically homogeneous and physically it has a boundary to distinguish it from something else, we can call it as a phase. So whether you call gas as a phase or a state, it does not matter. You can separate a gas from a liquid, there is a boundary between them. So now if I want to put gas onto this free energy diagram, how does it look like? how should it look like? One is, now I am trying to compare solid, liquid and gas. If I look at H and call it as H of S and H of L and H of G, and similarly I talk in terms of entropy, entropy of the solid, entropy of the liquid, entropy of the gas. Compare all of them. Among all these, which one should have the highest enthalpy? Gas, obviously, because integral Cp dt, if I look at it, the Cp of the gas should be higher than the Cp of the liquid and in turn higher than the Cp of the solid, and similarly entropy also, entropy of the gas should be higher than the entropy of the liquid and that of that. So as a result, if I now I am plotting the free energy of liquid and solid, I have already plotted. Now if I want to superimpose free energy of the gas on this, what should it be, the nature of that curve with respect to these two curves? Top, yes, and then what about its slope? It will be steeper, it will be steeper curve. So and as a result, and also now if I look at it should intersect the liquid somewhere, and that is what will be the temperature where the gas intersects the liquid. What would we call that? As the boiling point. So if you look at it, so you should have, if I extend that, it would be something like this, where it intersects the liquid curve at some point, it will be steeper. In principle I am just simply doing schematic diagrams, one can actually calculate all of them. What you need to calculate the free energy? Yes, what is the fundamental quantity that you need? Cp. As long as you know Cp as a function of temperature, one can simply integrate. If I know the Cp function, a plus bt plus c to the minus 2, what are the ABC values for a given material over a certain temperature ranges? Interestingly, if you carefully observe it, if I take Cp of a solid and that particular function with the ABC values, these ABC values will not remain the same for the same metal when I go from solid to liquid. It will have different ABC values, because the rate at which Cp changes with temperature in a liquid will not be same as the rate at which it changes with temperature in a solid, because atomic vibrations in a solid will be different from atomic vibrations in a liquid. So similarly in the gas, so the same, that is why whenever you go to a handbook and look for Cp values, there are large number of handbooks which will talk about Cp values. For example, Hultgren is one of the very popular handbook which will give you, and CRC handbook is another handbook which will give you the thermodynamic parameter, Cp parameter. Even if you go to simple book like Smithell's metals handbook, Smithell's metals handbook also gives you for all metals the ABC values for the Cp, and of course if necessary D value also, and these values they always tell you this is the range over which these values are valid, temperature range, and once you cross that particular temperature range these are not valid, you have to use another values of ABC. So as long as I know these values of ABC and I know the Cp function, I can happily integrate it, get the H, get the S, and once I get these two, I can calculate the G and plot it as a function of temperature. So whatever schematically I am drawing, these are all calculatable, and people have been doing. In fact, there is a journal which is dedicated for this. Have you heard of a journal where people do a lot of thermodynamics? There is a journal called CalFAD, calculation of phase diagrams. So where all the phase diagrams that we know in standard handbooks have been calculated using thermodynamic principles. What is the connection between the thermodynamic principles and phase diagram, we will see as we go along in this particular course itself. One can, in principle, any phase diagram that you see in a handbook. By the way, how do people get phase diagrams? Have you seen a phase diagram like iron carbon phase diagram? How did people get that phase diagram? How do you do, you mean you will do a high temperature XRD? DSC, how can it tell you what phases are there? But XRD you are doing it by cooling it back to room temperature only, isn't it? Or are you doing XRD at different temperatures? Change in resistivity. Anything else? Yeah, that's what, you can heat the sample to different temperatures, no problem, but at that temperature what phase is present, if you want to know, the only way to know is doing a high temperature XRD. If you cool back and then do a room temperature XRD, you do not know whether that phase has transformed to something else during this cooling. In most of the phase diagrams we see this happening. Most of the time the phase diagrams that we see regularly in our phase diagram handbooks, particularly the liquidus and solidus, is obtained by a particular method. Forgetting about solid state transformations, cooling curve, that is what is called thermal analysis. So if you draw a cooling curve, temperature versus time, heat the sample to a higher temperature above the melting point, cool it, and then you see what is called a changes in the slopes at the liquidus and at the solidus, and from that we get, if I can do this for various compositions, I will be able to get what is the liquidus, what is the solidus. Then coming to what about solid state transformations, let us say in iron carbon diagram we have a eutectoid transformation, we also have gamma becoming alpha. How do I get these things? That is where you can use X-ray diffraction. If you have read X-ray diffraction, there is a chapter in Quality which talks about how to get phase diagrams, particularly the solvus lines, how to get solvus lines using the using the XRD. So one can do it, but what I am saying is whatever you have generated from the cooling curve analysis, which is what we see in all the phase diagram handbooks that you see, most of them, excepting in cases where experiments are difficult. For example, if you are talking about a radioactive element, it is not so easy to do an experiment, you have to do it under very controlled atmosphere. If an element has a tendency to oxidize, you can still do a phase diagram measurements by melting and casting and doing cooling curve analysis in vacuum or in organic atmosphere. But some of the elements which are not stable elements, which have a very half life being very small, some of the radioactive elements, how do I do them? Phase diagrams. Or in some cases where the melting point of one of the metal is so high, for example think of tungsten, I want to generate aluminum tungsten phase diagram. How do I do it? I cannot melt tungsten, I do not have crucibles available where I can melt tungsten, because tungsten melting point is 3400 degrees or so. So the only way to do in such cases is this kind of calculations. So what we do is I can generate the phase diagram on the aluminum side of the phase diagram, because aluminum can be easily melted, no problem. So aluminum tungsten phase diagram on the aluminum side you can generate experimentally, do thermodynamic calculations and see if the thermodynamic calculations, the phase diagram that you get from the thermodynamic calculations fits well with the experimental phase diagram, and if the fit is good, then you get a confidence on the thermodynamics, and then assume that I can extrapolate it towards the tungsten side. And a lot of people do this, the whole CalFAD journal is dedicated for this kind of things, and people do various, and we are talking of simple binaries. Life is not just binaries, even steel for that matter, very rarely you use a binary steel which is simply iron carbon. We have so many elements in steels. You go to a stainless steel, you have additional elements. You talk about a superalloy, you have so many elements there, nickel based superalloy. So then how do I do experiments? It is not easy to find out the phase diagram for a 4 component system doing experimentally. If you want to take every 1% of the element and do a thermal analysis, you can imagine your whole life will go for that. That is when multi component systems particularly they try to do experimentally and thermodynamics. We will see it as we go along. So this is what we talk about, what is called the boiling point. So because the free energy curve for the gas will be different, this is, I can call it as a gas, and I can talk about wherever this gas intersects that of the liquid, I can call this as TB. Now, if you carefully observe, there is one more interesting intersection here. What is the other intersection? Where the gas is intersecting the solid, that is this. In principle, this tells me that if I can take a solid, keep on heating it, and this solid does not become a liquid for some reason, that solid in principle, the moment you reach there, beyond that temperature, the solid will have a higher melting higher free energy than that of the gas. So, that solid should catastrophically start becoming a gas, sublimate. For some materials, the sublimation temperature can be below the boiling below the melting point, so that the solids directly sublimate without even becoming a liquid. There are many cases like that. So, where these intersections are there, that is going to give you idea of this. So, this is what is called a metastable state, metastable transformation. There are cases where things like that can happen, particularly when you come to nanomaterials. Many cases you can see things like that happening, we will see as we go along. So, you can see that kind of. So, if at all I have to call it, I would call it as a sublimation temperature Ts, where if solid is remaining, you may say why should a solid remain without melting. For some reasons, if I am let us say heating the solid very rapidly, there is no time for the liquid to nucleate. All these are hypothetical cases, of course, there is a possibility. And of course, this whole phase the free energy diagram can be affected by pressure, which is what we will see right now, and then all these temperatures can even change with pressure, and that is what is called the Clausius-Clapeyron equation. We will try to see how does it come to. All of us have seen in the last class that G dG is VdP minus SdT, am I right? Okay. And what is the definition of equilibrium in a single component system that we have defined in the last class? Correct. The definition is G of liquid is equal to G of solid, or delta G is 0. This is the definition of equilibrium. For any unary system, we call them as unary systems, single component systems, we can use this. And if this is the case, if let us assume that solid is becoming a liquid, then I can write this expression for both solid and liquid. So, I can write that dG of a solid can be written as Vp, V of solid, S of solid into dt. I can also say dG of the liquid should be equal to V of liquid into dP minus S of liquid into dt. Okay. And at the transformation temperature where the solid is becoming a liquid, both of them should be equal, and if I equate both of them, then you would come up with an expression that it is like this is equal to this. If this is equal to this, I can say Vs minus Vl into dP should be equivalent to what? Yes, this goes that side, Vs minus Vl. So, this should come this side. So, S should be equivalent to Ss minus Sl into dt. Okay. So, if this goes that side, that comes this side. So, I can now write it as dt by dP is equal to delta S by delta V. Where delta S is Ss minus Sl and delta V is Vs minus Vl. And what is this dt by dP means? dt by dp is the rate of change of transformation temperature as a function of pressure is equal to this. So I can simply say that this is equal to that, and in principle the delta S can also be correlated to delta H. We can write it as delta S is equal to delta H by Tf. Delta any problem? Okay, this is delta V, sorry, you are right, this is delta V by delta S, correct, sorry for the mistake. So what it tells us is that the rate of change of melting point, in our case it is a melting point, it can be for any transformation, it can be alpha iron transforming to gamma iron, it can be gamma iron transforming to delta iron, it can be a liquid transforming to the gas. For any such transformation, the rate of change of transformation temperature with pressure is going to be this, and now depending on the sign of it and the magnitude of it, you would see the sign of dt by dp can be either negative or positive or highly negative or highly positive. For example, take up this particular case of aluminum. In case of aluminum, if I look at delta V is Vs minus Vl. Vs minus Vl for aluminum, is it positive or negative? At the melting point, if I look at what is the volume of the solid and what is the volume of the liquid, it is negative. In fact, that is why if you carefully observe, you would have seen, if I plot V versus T, you would see a step like this. Have you seen things like that? And that is what in fact all those foundry people talk about shrinkage. When a liquid becomes a solid, there is a shrinkage, because this is liquid, this is solid, and this difference is a delta V, and in fact we give what is called a shrinkage allowance for the patterns, excepting in few cases where we know that there is no shrinkage or there is even a possibility of an expansion. Grey cast iron. Why in a grey cast iron there is no shrinkage? The graphite has got a lower. Yes, graphite has a lower density. In a grey cast iron, when a liquid is solidifying, you get gamma plus graphite during the solidification, and graphite has a much lower density than that of the iron. As a result, it occupies more volume. So there is a volume expansion. In fact, depending on how much of graphite is coming, you may have a zero, a lower shrinkage, or zero shrinkage, or even an expansion, depending on what is your composition of the cast iron and how much of graphite is coming. One can in principle see even an expansion. That is why we even some cases of grey cast iron we give what is called a negative allowance. In pattern allowances you would have heard about it. So this is what is it as far as delta V is concerned. Similarly, you can also plot H versus T and see a similar thing. This is for the liquid, this is for the solid, and what we call this, what is that? Latent heat of fusion. That is why whenever a liquid is transforming into a solid, solid at that temperature at the melting point cannot take all the enthalpy that is contained in the liquid, and liquid has an excess enthalpy. This excess enthalpy has to be given out, then only the solid can transform to a solid, the liquid can transform into a solid. Otherwise liquid cannot transform into a solid unless you remove that excess heat, and that is the reason why when you pour a liquid metal into a mold, the mold is the one which extracts all this heat. And that is the reason why if you carefully observe what is called, if I draw this T versus T, you would have seen this plots. Why do you see this? It is because there is certain delta H associated with a liquid to solid transformation. when the liquid is becoming a solid, and this is where liquid transforms to solid, and there is certain delta H associated with this transformation, and depending on the rate at which the mold is extracting the heat, it needs certain amount of time. You can simply see that if I want to know what is the delta T, time required for the solidification, that can be found out by what is the delta H of fusion divided by dH by dt, what is the heat extraction rate. If I know the heat extraction rate that the mold has, and which basically depends on the conductivity of the mold, I can find out what is the heat extraction rate, and if I divide the enthalpy of fusion with this, what you get is this is small t, not capital T. In thermodynamics always capital T is temperature, okay, small t is the time, so always remember. So if I divide this with this, what you get is the time. So in principle, in any solidification process, what is the time of solidification? When somebody talks about it, the time of solidification depends on two parameters. What are the two parameters? One is heat of fusion, second is the rate of heat extraction. So if I pour the same liquid metal into a sand mold or a permanent metallic mold, you would see the solidification time comes down when I pour it into a metallic mold, basically because I am increasing the denominator. I am not changing the numerator, because the same metal is being solidified, because I am increasing the numerator, it changes. So you can see this happening. Coming back to this, so we know that for aluminum delta V is negative. What about delta S? What is delta S in this particular case? Change in entropy from where to where? So it is SS minus SL, we have already defined it. So SS minus SL is negative, it cannot be positive, it cannot be positive, so it is negative, and because both are negative, this has to be positive, the ratio has to be positive. That what does it tell you? It tells you that if I increase the pressure, the melting point of aluminum will increase. If I decrease the pressure, the melting point of aluminum will decrease. That means the same aluminum, instead of melting it at atmospheric pressure, if I melt it at 10 to the power minus 6 torr vacuum, it should melt at a lower temperature than 660. Unless I know this Clausius-Clapeyron equation, I would not be able to know that. This is a very, very crucial thing, and all those people who do what is called secondary steel making, they should know this, otherwise they will not know to what temperature they should heat the steel to melt. All the secondary steel making is vacuum refinement. So all those people who do vacuum refinement of any metals and alloys, they should know what is the rate of change of the melting point with pressure, so that at the particular vacuum level that they are maintaining, what is the melting temperature to which. Otherwise, either if you assume that the melting point is the same as the atmospheric pressure, you are unnecessarily wasting energy, because you know pretty well that it would be lower, excepting in some cases where it will not be lower. That is, one case can be, just now we have seen grey cast iron, where the delta V will be positive, but delta S is negative. So the ratio is negative. That means in case of grey cast iron, so if there is a difference between melting a white cast iron and a grey cast iron. If I am taking a grey cast iron and melting it, the rate of change of melting point of grey cast iron with pressure is different, and it is negative there, whereas in case of white cast iron, the rate of change of melting point with pressure is positive there. The melting point will increase with increasing temperature, whereas here it decreases with increasing pressure, or it increases with decreasing pressure. So if I melt a grey cast iron in vacuum, its melting point will be higher than its usual melting point, whereas if I melt a white cast iron in vacuum, its melting point will be lower than the usual melting point. Similar thing we also see in case of water and a few other metals. For example, few metals such as antimony, bismuth, they all have delta V being negative, solid to liquid. Whenever I say delta V, you need to know which minus what, and in thermodynamics we always take the product minus the reactant. Whenever we are talking of any delta V, any change in any property, any thermodynamic property, it is product minus the reactant. So you need to know which direction is the reaction taking place and the product minus reactant. So in our case, let us say we are talking of liquid to solid transformation, then it is Vs minus Vl. If it is solid to liquid transformation, it is Vl minus Vs. But because we are consistent in our direction, whatever you take here, if you take the same thing here, there is no problem. Even for example, here you interchange here and also interchange here, there is no problem, the sign is going to be the same. So you will see that this is very crucial. And if you want to see from another point of view, whenever I take a solid and start heating it under pressure, let us say, we know pretty well that pressure and volume are always inversely proportional. So under pressure, always the phase that is more stable is the one which occupies low volume. Thermodynamically, whenever I apply a pressure, the phase that occupies low volume, less volume, is more stable. What among the liquid and solid in case of aluminum, if I am considering aluminum, what has low volume? It is a solid. So solid is more stable. It wants to be stable up to higher and higher temperatures as I put more and more pressure. And what does it mean? It means the melting point increases. And that is why if you look at this curve once again, I can, if I take this as liquid, this as solid, when I apply pressure on the solid, you would see the solid becomes more stable under pressure. So the free energy of the solid decreases, and when the free energy of the solid decreases, imagine it is decreasing. This is at atmospheric pressure, this is let us say at high pressure, 2 atmosphere, 3 atmosphere, whatever it is. And what does it influence? You will see the intersection temperature has changed. What has happened? The melting point has increased when I apply a pressure. So you can see, you can use free energy diagrams to explain all these things, and as we go along we will see in this course that we can use free energy to explain every phenomena that we see in our material science, and we will see. And the same thing holds good if you take a graphite and apply pressure. Why do you see that diamond comes? It's just because of that. And diamond occupies less volume when compared to graphite. It is more close packed structure. Diamond cubic is much more close packed structure than graphite, and that is the reason why under pressure diamond is more stable, and that is why you find diamond at deep inside. Of course temperature is also important, high temperature, high pressure. In fact, people have done experimentally, there are many physicists who have developed high pressure dyes, and they have taken materials and applied very high pressures, and pressures of the order of few gigapascals and things like that, and could show that the structures of materials change. And we can in principle talk in terms of a phase diagram where you have both temperature and pressure. And if I want to see such a phase diagram, the simplest phase diagram that we all know about is that of water. Let us look at water phase diagram. All of you might have seen it, but let us look at it from this thermodynamic angle right now. For example, if I plot temperature versus pressure, I can show this is solid, this is liquid, this is gas. And these lines that you are seeing are the transition temperatures from one state to the other at various pressures. For example, if I look at this line, what does this line tell you? This line is where the solid is transforming to gas, that means it is a sublimation temperature Ts. How does Ts change with pressure? You can see from here, as I increase the pressure, Ts is increasing. Why? Because if I again go back, dt by dp is delta V by delta S, and for a solid to gas transformation, V of gas minus V of solid is positive, S of gas minus S of solid is positive. So, the whole ratio is positive, so the slope has to be positive. Similarly, if I look at this line, it is a liquid going to gas, that means it is a boiling point, and for the same I can say liquid going to gas. Again you would see that the dt by dp has to be positive, that is why you see a positive curve, excepting this one single line which is negative, which has a negative slope. The reason is when a solid is going to a liquid, delta V is negative, whereas delta S is positive for water. This is for water we are doing, or I would not call it as water, I will simply call it as H2O, because water is one state of matter of H2O. So, if I am talking of the phase diagram of H2O, it looks like this, and in principle I can draw phase diagrams of every metal, every single component system. This is the phase diagram of single component. By the way, you may ask me, sir, why should I call H2O as single component? There is H and O there, there are two components there, but why should I call it as a single component phase diagram? Yes, when it is melting or solidifying or evaporating, it does all this as a single entity. H2O does not split into H and O. When ice is melting, okay, it does not split into H and O and then melt, it melts as a single entity. This is what you would see even when we come to normal phase diagrams also. Many intermetallic compounds, when they melt as one single compound. For example, if I take as Fe3C, Fe3C actually melts as a single compound. That is the reason why phase rule, when we are doing P plus F equal to C plus 1 or C plus 2, we will try to see it in a minute, and this phase rule has to be looked at it carefully, because there is a term called C comes, number of components comes. This number of components you have to understand it carefully, otherwise you get into troubles in terms of the phase rule. So, we will try to see that in a minute now.
So, for the liquid to gas transition,
liquid to gas transition, dp is negative. dp, why we are talking of dp? We are not talking of dp negative. What we are talking is, if I change pressure, if I keep on increasing pressure, pressure is increasing in this direction. Whether the melting point would decrease or increase, or whether the transformation temperature would decrease or increase is what we are looking at, and that depends on these two, isn't it? So, what I am saying is, if I increase the pressure, whether the liquid to gas transformation temperature, which is the Tb boiling point, this is the Ts, this is the Tm, whether the Tm would decrease or increase. Here you can see Tm is decreasing with increasing pressure. This is the temperature which is increasing in this direction. This is the transformation temperature, I would call it as Tt. This is not simply temperature, it is a transformation temperature we are talking about, the temperature at which one phase is changing to another phase. That is what we are plotting here. If you look at it, then you would see that the yes. Which phase will be there? Yes, it is a question of I do not know whether you got worried about this any time. Whenever you take a metal like aluminum, I think day before yesterday somebody was asking, I was talking about it. If you are ever bothered about why should a liquid, when it becomes a solid aluminum, know that it should become an FCC aluminum, and if I take a iron when it becomes a solid, it becomes a BCC iron, And if I take a zinc, the moment I melt zinc and solidify zinc, it becomes a HCP zinc. How does this liquid know? Liquid is random atoms, atoms are randomly arranged. Such a random arrangement of atoms suddenly at the melting point changes into an ordered structure, ordered arrangement of atoms, and then that ordered arrangement of atoms has a fixed crystal structure, and this structure changes from material to material. And how does this liquid come to know about it? And that boils down to a problem in thermodynamics, what we call it as what is the ground state for a particular material at any given temperature. The ground state for a particular material, ground structure, or that means the stable structure, is the one which is what you will obtain when a liquid transforms to a solid. But this structure, what is the structure, again is going to depend on the electronic configuration. So in principle people have done, if you go to a book by name Kaufman and Bernstein, I am not very sure about the spelling here, but Kaufman is very famous. You look for Kaufman, the title of the book is Calculation of Phase Diagrams, and if you look for in that book, the first chapter is dedicated to this, what we call first principle calculations of what should be the structure of a particular metal at a given temperature. For example, if I try to calculate what should be the free energy of FCC aluminum, HCP aluminum, BCC aluminum as a function of temperature, if I do this calculation knowing how the electronic configuration in aluminum is, though it is easy to say, but it is more difficult to calculate, because all first principle calculations for more and more number of electrons, if you have the calculations become more complicated, because you have to take multi electron interactions. People are able to do it for hydrogen, helium, but beyond that the calculations are more and more difficult. Aluminum, if you know the atomic number we know, so the number of electrons we know, so each electron interacts with the other electron, so you have to consider that. But if I can calculate this, I would be in a position to find out what should be the structure, what should be the free energy of different structures, and look at those free energies. You would find out that for aluminum, FCC structure would have the lowest free energy. It is ultimately the free energy. The only way is how do I calculate the free energy for a particular metal. As long as I can calculate it, you would see that it is what happens. Then the question is, how does this liquid know? Yes, the FCC has the lowest free energy for aluminum. Why should this liquid become FCC aluminum then? It has a lower free energy, but inside liquid there is no FCC structure. How does suddenly at melting point FCC structure comes in? That is where you need to understand that liquid always has what is called a short range order. This is different from how do I differentiate a solid from a liquid and a gas. This is what differentiates. A solid has a long range order, a liquid has a short range order, and a gas does not have. In a gas you do not see a short range order clusters. In a liquid you always have clusters. Within a cluster you have a periodicity, you have a unit cell, and these clusters are of different sizes. You have different sizes clusters. This is what we call them as embryos inside the liquid, and when one of the cluster attains that size of a nucleus at the melting point, that nucleus starts growing, and all other clusters are still there inside the liquid, but they do not grow. Only that which has a size of the nucleus is the one which starts growing. So in every liquid, in fact one can even calculate thermodynamically, okay, what is the size of that cluster as a function of temperature. All this you must have done in a nucleation kinetics. Yes.
When I go to gas, there is no orderness.
When I say no orderness, molecules are there. I am talking of in case of metals, let us say there is a single atom. So there are only single atom molecules inside the gas of aluminum, and there is no clusters at all that I can talk about as a particular unit cell.
So the gas is aluminum is sublimated to the solid aluminum.
Correct.
So can I transform FCC to the BCC aluminum?
In principle there are cases where people have done, when people have done metastable transitions, when you quench a gas, there is a possibility that you overtake one of the stable state, possibly whenever some of the structures, stable structures, if they are very complicated structures. For example, there are cases which as we go along we will see what are called metastable phase diagrams. For example, a simple thing like Fe3C, which we have seen last time. Why does Fe3C form? Why not graphite form? Because this splitting takes a long time, so the system prefers to that. And there are cases where some of the intermetallic compounds have a complicated crystal structure, and as a result if I take a liquid and quench this liquid instead of forming that intermetallic compound can form some other a simple structure, or can even form a glass. That is what we see, a glass formation. We will see as we go along. So this kind of metastable states are possible, and I will show you a few metastable phase diagrams where instead of a stable state which is available in the phase diagram, something else comes out. And that is what I have shown you earlier also. In case you can stabilize a solid beyond the melting point, it would become a gas, and this gas is now forming at a temperature below the boiling point. In principle, below the boiling point it should not have gas. So that is what you would start seeing. So this is possible, and if you go to that, one can find out that. So in principle one can talk about what are the states that are possible. And if I continue here and look at, we have now seen a slope. We have only talked about the positive or negative of the slope only. We have not talked about what is the absolute magnitude of the slope. Absolute magnitude depends on delta V by delta S. As long as I know what is the delta V, what is the delta S at different pressures, then that means I should have a knowledge of how V of solid changes with pressure, how V of liquid changes with pressure, and if I know that, in principle at different pressures, if I know what is delta V and what is delta S, in principle I can calculate that. So this, though I am plotting it as a straight line, it may not be a straight line. And similarly, when we draw these two as straight lines, they may not be straight lines. In principle, V as a function of temperature might increase, not as a straight line. Yes, that is what we are going to come to. Possibly today we will not discuss. If you know the phase rule, so next class we will talk about the phase rule, where we will be able to understand this particular triple point, because at this triple point you would see the three phases are coexisting, and when the three phases are coexisting you will see that what is called the degrees of freedom becomes 0. So this is fine for a single component system. Now what happens if I take a binary system? Let us say this is for aluminum phase diagram, accepting that for aluminum this is not the correct phase diagram. What should be the correction that I should incorporate for aluminum? Yes, this line should be like this. That is the only change. Of course, when I say that is the only change, the actual slopes in water, in H2O will be different from the actual slopes in the aluminum, but the aluminum, all the three slopes will be positive. All the three slopes will be. So aluminum, iron, most of the metals where you do not have that anomaly of the delta V, the volume of the solid being higher than the volume of the liquid, as long as that anomaly does not exist, this is true, we can do that. And now the moment I say a binary, I have to add something more there. If I am talking of a two component system, let us say aluminum copper, I have additional element there. So this phase diagram I have to add one more axis there, which is nothing but the percentage of copper. So it becomes a ternary kind of diagram, a three dimensional diagram, and in that three dimensional diagram we will start working on it. We will talk about it in the next class, okay, how to do such a thing. I am stopping because it has come to 0 there. Can we continue even after it goes to 0? No problem, we will stop, okay. So that is why I will follow that. this is the problem, you know, for a teacher. No teacher wants to stop. Yeah, tell me. Correct, correct. See, because the Cp as you know below the Debye temperature at very very low temperatures, it is the electronic configuration contributions come into picture. Okay, at a higher temperature it is more of atomic vibrations. Very low temperatures, you know, closer to 0 degree 0 Kelvin, actually we do not actually have much of atomic vibrations, but it is the electrons inside the atoms, they tend to vibrate, and that is the reason why you get, but that value is too small, and as a result Cp is very small, but the rate of change of Cp with temperature will be different, because those vibrations are going to be different from that of the atoms. So there are different expressions that are available for the Cp at low temperatures, at higher temperatures. One can calculate it, they are available. You have to go to the standard handbooks and for different materials that are, but most of the cases, because we deal with metals above room temperature, we do not actually talk about that contribution at all. That contribution is insignificantly small when compared to atomic vibrations at temperatures above the atmosphere room temperature, and accepting physicists, typical metallurgist or a mechanical engineer or a chemical engineer is not really concerned about such low temperatures. Okay, we will stop.